Welcome all. In this lecture, I am going to discuss about numerical problems regarding second law of thermodynamics. Basically, these problems are related to the heat engine and refrigerator. So, this is in continuation of the earlier lecture. In the earlier lecture also, I discussed some numerical problems regarding the heat engine and refrigerator. So, these particular problems are from the textbook Thermal Physics with Kinetic Theory, Thermodynamics and Statistical Mechanics by S.C. Garg, C.K. Ghosh and R.M. Bansal. So, let us discuss the first problem. Consider four heat reservoirs A, B, C and D. The efficiency of a reversible engine working between A and C is half of the sum of the efficiencies of the same engine when it is operated between A and B and between A and D. Calculate the temperature of reservoir C. So, if you carefully look at this problem, so you see that there are total 4 reservoirs A, B, C and D. Now, the engine can work between any two of the reservoirs. So, suppose it is working between A and C. So, if the engine is working between A and C, then the efficiency of the engine is half of the sum of the efficiencies of the same engine when it is operated between A and B and between A and D. So, in that case, what will be the temperature of the reservoir C? To solve this problem, let us denote the temperature of the heat reservoirs as TA, TB, TC and TD. So, these are the temperatures of the reservoirs A, B, C and D. For a reversible engine, we know the formula of the efficiency eta is equal to 1 minus T2 by T1. This formula I have already discussed in the earlier lecture. Now, here the temperature T2 is the temperature of the sink, that is the cold reservoir, and T1 is the temperature of the source. Source means these reservoirs, that is A, B, C and D. Now, in the present case, it has been given that if the engine is working between A and C, so its efficiency we are denoting as eta AC. And if the engine is working between A and B, then efficiency is eta AB. And if the engine works between A and D, then the efficiency is eta AD. So, according to the problem, eta AC is equal to half of eta AB plus eta AD. This is given. Now, if we apply the formula of the eta, now you see that this is eta AC. So, I can write 1 minus TC by TA is equal to half of eta AB, that should be 1 minus TB by TA plus 1 minus TD by TA. Now, you just look at this particular thing, that is eta AC. So, the engine is working between the reservoirs A and C. So, eta AC is equal to 1 minus TC by TA. So, here TC is the cold reservoir and TA is the hot reservoir. So, we are using the notation in this way, that is, if this is eta AC, then I will write 1 minus TC by TA. And this is same for all the eta, that is eta AB is equal to 1 minus TB by TA, eta AD is equal to 1 minus TD by TA. We are assuming in this way. So, by rearranging, I can write that is TC is equal to half of TB plus TD. So, temperature of the reservoir C is equal to half of TB plus TD. So, this is the required answer. The temperature of the reservoir C is equal to half of temperature of the reservoir B plus temperature of the reservoir D. Now, next problem, an inventor claims that his heat engine delivers work at the rate of 1 kilowatt and absorbs energy at the rate 65 kilojoule per minute from a source at 1127 degree centigrade when the temperature of the sink is 27 degrees centigrade. Is the claim justified? So, we have to analyze, that is the claim is justified or not. So, how to proceed? Now, at first we will write the formula of the efficiency eta, that is equal to 1 minus T2 by T1. So, T2 is the temperature of the cold reservoir and T1 is the temperature of the hot reservoir. So, according to this problem, if you convert these temperatures into the Kelvin unit, so T2 is equal to 300 Kelvin and T1 is equal to 1400 Kelvin. So, you can calculate eta very easily. So, this is the value of the eta. The efficiency claimed by the inventor is equal to W by Q1. Now, what is W? W is basically the work done. You see that in this particular problem, it has been mentioned that the engine delivers work at the rate 1 kilowatt. So, 1 kilowatt means 1000 watt, and 1000 watt means 1000 joule per second. And Q1 means that heat absorbed. You see that it has been mentioned, that is absorbed energy, that means absorbed heat energy, that is 65 kilojoule per minute. As it has been mentioned per minute, so we are converting into the second unit, that is per second. So, 65 by 60, and this is kilojoule. To convert into the joule unit, we have multiplied 10 cube. So, ultimately we have obtained, that is as per this particular data, the efficiency is 0.92, but the maximum possible efficiency of the Carnot engine eta is equal to 0.78. That is, if we use the source temperature and the sink temperature, these values, if we use these values, then in that case the maximum efficiency, that is the efficiency of the Carnot engine eta, that must be 0.78. But the inventor claims that the engine can deliver work at the rate of 1 kilowatt and absorbs energy at the rate 65 kilojoule per minute. So, from that data, it appears that the efficiency of the engine is 0.92 and it is greater than the efficiency of the Carnot engine. But we have already read in the text that there is no engine whose efficiency is greater than the Carnot engine. So, this particular claim, that is this particular data, energy data, is not true. So, this claim is not justified as per the second law of thermodynamics. Next problem, a doctor practicing in Delhi preserves some medicines at minus 23 degrees centigrade. If a refrigerator used for this purpose has a 200 watt compressor, how long will it run if the outside temperature is 27 degrees centigrade and the cooling rate is 5 into 10 to the power 4 kilojoule per day? So, at first you just focus on the problem, that is what data is given here. You see that the temperature inside the refrigerator is minus 23 degrees centigrade, because the doctor preserves the medicine at this particular temperature, minus 23 degrees centigrade, and the compressor of the refrigerator, the watt value is 200 watt. This is the watt value. So, how long will it run if the outside temperature is 27 degrees centigrade? So, the temperature of the surrounding, that is where the heat will be rejected, that temperature is also given. This is 27 degrees centigrade, and the cooling rate is also given, that is 5 into 10 to the power 4 kilojoule per day. So, what is the problem actually? This problem basically asks about how long will the refrigerator run. So, if we use such a compressor and such a cooling rate, so how long the refrigerator will run, that is the problem. And if the same refrigerator is used in Burma, in Thor desert, where the room temperature on a summer day is 47 degrees centigrade, Then estimate the fraction of the time of the compressor runs for the same cooling rate. So the second case is that we are using the refrigerator in Thor desert where the outside temperature is very high. You see that in Delhi the outside temperature is 27 degrees centigrade, but in Thor desert the outside temperature is 47 degrees centigrade. So this temperature is quite higher, but you are applying the same refrigerator at the same cooling rate. So the point is that what fraction of the time the compressor runs. So in this regard, it should be mentioned that the compressor of the refrigerator does not run for all the time. That is, it runs for a particular fraction of the time. So we have to calculate that fraction of the time for which the compressor runs. So this problem is very interesting problem. Now, in the text we have read that is the coefficient of performance is given by this equation omega is equal to TL by TH minus TL. So, TL means actually the temperature of the uh, cold reservoir, or we can say that it is the temperature inside the refrigerator. TL low, L means low, actually low temperature, and TH means T high, which is the temperature outside. So this is TH and this is TL. So this is the definition of the coefficient of performance, and as that is as given in the problem in case A, that is in Delhi, and the temperature inside the refrigerator is minus 23 degrees centigrade, and in Kelvin unit it is 250 Kelvin, whereas TH, that is the temperature of the surrounding, is 27 degrees centigrade. That means TH is equal to 300 Kelvin. So the coefficient of performance omega is 5. Now the coefficient of performance is also defined as omega is equal to QL by W. It has been mentioned in the text, that is, this is another formula of the coefficient of performance, where W is the work done and QL is the heat. QL is the heat that is being rejected. So as per this problem, you see that is W is, if omega is equal to QL by W, then W will be QL by omega. Now omega we have already calculated here, this is 5, and QL, that is the heat. Now you see how the heat is given here, that is it has been mentioned in terms of the cooling rate. Cooling rate means actually 5 into 10 to the power kilojoule heat is being rejected from the refrigerator to the surrounding per day. You see this 5 into 10 to the power kilojoule of heat energy per day that is being rejected in the surrounding. So this is basically the amount of heat Q. So we have written 5 into 10 to the power 4 kilojoule day inverse, means per day, divided by 5. So this is the work done W, that is 10 to the power 4 kilojoule per day. Now you see that is what is the wattage of the compressor. This is 200 watt. Now as the wattage of the compressor is 200 watt, so if the compressor runs all the time, throughout the day, then how much work will be done? We can calculate that. So 200 watt means 200 joule per second. So per second 200 joule work is done. But 1 day means 24 hours into 3600 second. So in a particular day, work done by the compressor is this one. This is the work done by the compressor. Now we know that the compressor does not run all the time. So what is the fraction of the time that the compressor runs? So how we can calculate? We can calculate from this particular formula. That is, you see that from this formula we have already calculated work done, that is heat energy which has been rejected by the which has been rejected in the surrounding, divided by omega. So this is the work done W. We have already calculated that this is 10 to the power 4 kilojoule per day. This is the heat energy rejected, and this is the total work done by the compressor in a day. So if this is the total work done by the compressor in a day, So the fraction of time the compressor runs, that will be the ratio of this W, that is this work, divided by the total work done. So now 10 to the power 4 kilojoule means 10 to the power 7 joule per day unit. It is in per day unit, and this work is also done in a particular day. So we have divided 10 to the power 4 kilojoule by 17280 kilojoule. So this fraction comes to 0.57. So this is the fraction of time that the compressor runs. Fraction of time means if you consider 1 second, then the compressor runs 0.57 second. So this is the actually fraction of the total time that the compressor runs. Now if the same refrigerator is working at third desert, so in that case what will be the value of the omega? Because you see here in the second case the temperature is different. Inside temperature is same, but the temperature of the surrounding is different. That is why the value of the omega will be different. This is 3.57. Again we will apply the same formula of W, that is QL by omega. So omega is equal to QL by W. Then we have calculated W, that is for the second case. So for the second case the value of W will be this one. So the fraction of time for which the compressor runs in the second case, so that will be that is the work done W divided by the total heat rejected in a particular day, that means this one 17280. So in the second case the fraction appears 0.81. So you see that this is quite common, because as the refrigerator is working in a desert where the temperature of the surrounding is very high, so in that case the refrigerator will run for a greater time, because this fraction is higher than the fraction which we have calculated for Delhi. So it is quite expected. Next problem, calculate the efficiency of a Carnot engine working between 1 to 7 degree centigrade and 27 degree centigrade. It absorbs 80 calorie of heat from the source. How much heat is rejected? This problem is very easy, because you see that here the temperature of the source and the sink is mentioned. So from that data we can calculate the efficiency eta. So this is our first task. We have calculated the efficiency eta, and in the next step what we will write, that is there is a different formula of the eta, that is W by Q, which we have already used in the previous problems. So eta is equal to W by Q. So W will be eta into Q. We have already calculated the value of the eta, and you see that here the amount of heat is given, that is Q is given. This is 80 calorie of heat. It absorbs 80 calorie of heat from the source. So W is equal to eta into Q. So 0.25 into 80 calorie. That means W is equal to 20 calorie. We have calculated the work done from this formula. Eta is equal to W by Q. Now there is another formula which we have discussed in the earlier lecture, that is W is equal to Q1 minus Q2, or Q2 is equal to Q1 minus W. Now you see that is here the Q1 is 80 calorie. Q1 is 80 calorie, that is the heat taken, because you see the statement, it absorbs 80 calorie of heat from the source. So this is heat taken, that is Q1, it is the heat taken from the source, and Q2 is the heat rejected. So heat rejected Q2, that will be equal to Q1 minus W. So Q1 is given in the problem. We have calculated W in the previous step, so we can calculate Q2, the value of Q2, that is 60 calorie. So it is absorbing heat 80 calorie from the source, and by this problem we have what we have seen, that is it is rejecting heat 60 calorie. So from this particular problem what we can say, that note that a low efficiency engine cuts two ways. So if the efficiency of a engine is low, then what will be the problem? Basically the first thing is that it causes wastage of fuel, that is you need more fuel to run this particular engine, and secondly it is uneconomical and degrades the environment. Why it degrades the environment? You see that efficiency of the engine is 25%, and that is why it is rejecting this particular amount of heat, 60 calorie of heat into the environment. So, this particular heat which is rejected in the environment, it basically degrades the environment. So, this is the that is understanding from this particular problem. A Carnot engine has an efficiency of 30% when the temperature of the sink is 27 degrees centigrade. So, you see that is the efficiency is given and temperature of the sink is given. Calculate the change in temperature of the source to raise its efficiency to 50%. Now, suppose you want to increase the efficiency of the Carnot engine from 30% to 50%. So, in that case, what should be the temperature of the source? So, this is very easy problem. You see that is, you know the formula of the eta, that is 1 minus T2 by T1, and in the first case the value of the eta is how much? This is 30%, means 0.3. So, I can rearrange this particular equation and I can write T1 is equal to T2 by 1 minus eta, where T1 is the temperature of the source and T2 is the temperature of the sink. T2 is given here, this is 27 degrees centigrade, means 300 Kelvin. So, from this equation we can estimate that the value of the T1 is this one, 428.6 Kelvin. In the second case, you want to increase the efficiency to 50%. So, in that case again we are using this particular formula, but we are writing as T1 prime, because in the second case the temperature of the source will be higher and that particular value we have to calculate. So, we are writing T1 prime in place of T, and temperature of the sink will remain same, that is this is 300 Kelvin, and for eta it will be 0.5, because in the second case the efficiency is 50%. So, you see from this calculation T1 prime is equal to 600 Kelvin, and previously it was this much, 428.6 Kelvin. So, how much we have to increase? The difference is 171.4 Kelvin. Next problem, a 100 kilowatt engine is operating between 1 to 7 degrees centigrade and 27 degrees centigrade. So, you see from the first sentence the data regarding the temperatures is given, that is temperature of the source and sink is given, and 100 kilowatt engine, that is the wattage value is given, from which we can calculate the work. Calculate the amount of heat absorbed, heat rejected and efficiency of the engine. So, we have to calculate several parameters like heat absorbed. Heat absorbed means Q1, heat rejected, that means it is Q2, and efficiency, that is eta. Now, we know the formula, that is W is equal to Q1 minus Q2. What is W? W is the work done, and another formula we also know, that is Q1 by Q2 is equal to T1 by T2. Now, T1 by T2 is given in this problem, just we have to convert to the Kelvin unit. So, from this data Q1 by Q2 is equal to 4 by 3. So, just we are rearranging this particular equation. So, Q1 by Q2 minus 1 is equal to 1 by 3, or Q1 minus Q2 by Q2 is equal to 1 by 3, but you see that is Q1 minus Q2, it is again W, because we know that is W is equal to Q1 minus Q2. So, from this equation, if we write Q1 minus Q2 is equal to W, then I can write 3 into W is equal to Q2. So, Q2 will be how much? Because you see that is W is given, actually this is 100 kilowatt. Kilowatt means 100 into 10 cube watt. So, that means 10 to the power 5 joule per second. So, Q2 will be 3, as it is 3 into W. So, 3 into 10 to the power 5, because W is actually 10 to the power 5, 100 kilo means 10 to the power 5 watt. So, Q2 will be 3 into 10 to the power 5. So, we have calculated Q2. Now, we know that W is equal to Q1 minus Q2. So, you see that from this formula we know the value of W, we know the value of Q2. So, we can calculate Q1 easily. So, Q1 will be W plus Q2. So, this is the value of the Q1. Now, you see that is heat absorbed per second is this one, Q1, and heat rejected per second is this much, 3 into 10 to the power 5. The efficiency of the engine is given by 1 minus T2 by T1. So, T2 and T1 is already given, so we can calculate efficiency also. The next problem, a heat engine working between two temperatures converts 1/8 of the heat supplied into work. If the lower temperature is reduced by 95 degrees centigrade, the efficiency is doubled. Calculate the initial temperatures of the source and the sink. So, suppose you consider a heat engine which is working between two reservoirs, and you particular focus on this particular sentence, that is, it converts 1/8 of the heat supplied into work. So, the amount of heat which is taken by the engine, 1/8 of the heat is supplied into the work. So, what is the meaning of this particular sentence? So, actually this is the value of the eta, because it converts 1/8 of the heat supplied into work value. So, if you read the text very carefully, then you will understand that this is basically the value of the eta. So, eta is equal to 1 by 8 is equal to 1 minus T2 by T1. This is the formula of the eta, but value of the eta is 1 by 8. Now, the point is that if you go through the next sentence, so it has been written that if the lower temperature is reduced by 95 degrees centigrade, the efficiency is doubled. That means, suppose the low temperature is T2 and you are lowering it further, how much? By 95 degrees centigrade. In that case, it is very clear that the efficiency will be increased, because you can increase efficiency either by decreasing the temperature of the low temperature reservoir or by increasing the temperature of the high temperature reservoir. So, in this particular case, we are reducing the temperature of the low temperature reservoir. So, naturally the efficiency will be increased. So, if in the first case the efficiency is 1 by 8, eta is equal to 1 by 8, in the next case this efficiency is doubled. That means in the next case the efficiency will be 2 into 1 by 8. 2 into 1 by 8 means 1 by 4. Now, if we apply the same formula, that is 1 minus T2 by T1, but in the second case we have to write T2 minus 95 Kelvin. Why? Because we are reducing the temperature by 95 degrees centigrade, but as this is the this particular fraction, that is T2 minus 95 by T1, so T2 minus 95 is the difference only. T2 is the initial temperature, the final temperature is T2 minus 95. So, when we will consider the difference, so in that case centigrade unit and Kelvin unit will be same. So, we can write T2 minus 95 Kelvin. So, 1 minus T2 minus 95 Kelvin divided by T1. So, T1 is the temperature of the source. Now, after simplification, I can write that is this is 1 by 8 minus 95 Kelvin by T1, or by solving it appears that T1 is equal to this much, 760 Kelvin. So, if T1 is this one, then I can write that is T2. I can write that T2 is equal to 7 by 8 into T1. Why 7 by 8 into T1? We are using this formula because this formula relates the temperature T1 and T2. So, from this particular relation, we can say that is, if we are able to calculate the value of T1, then we can also calculate the value of T2. So, this is the value of the T2. A Carnot engine has an efficiency of 0.5. So, efficiency is given while working between the source 400 Kelvin and a sink at T2 Kelvin. So, source temperature is given, sink temperature is T2. Calculate the efficiency of the engine if temperatures of both the source and the sink are increased by 100 Kelvin. Calculate the efficiency if the temperature of the source and the sink are reduced by 100 Kelvin. So, this problem is very easy. Suppose if you consider the initial case, so in the initial case the efficiency was how much? It was 0.5. Now, you just write the formula of the efficiency, that is eta is equal to 1 minus T2 by T1. Now, you see that is the source temperature is given and sink temperature you just write T2 as it is. So from this particular formula you can calculate T2. Now in the second case, what is happening, that is you are increasing the temperature of the source and sink both by 100 Kelvin. So you have to calculate the efficiency. Now you see that is as you know that temperature of the source and the sink, because in the initial case you have already estimated the value of the T2. T1 is given already. So in the second case you are increasing the temperature by 100 Kelvin. So you just increase the temperature of both T1 T2. So you can easily calculate eta by this particular formula. And in the last case you are reducing the temperature of the source and sink by 100 Kelvin. So again in the last case you can calculate the value of the eta prime. So in this way you can solve this problem. Next problem. A Carnot engine is operated in reverse order. That means it is working basically as a like a refrigerator. So the work input to the unit is 12 kilowatt. So 12 kilowatt is the work input, and coefficient of performance, COP means coefficient of performance, is 2.5. For cooling, calculate the ratio of temperatures within which the device operates. So as we intend to cooling, so what we have to do, we have to calculate the ratio of the temperatures. So now we know that coefficient of performance is equal to Q2 by W, that is heat extracted at low temperature divided by the work input. We have already used this formula in several problems. Now it is given that coefficient of performance is 2.5. Now what is the value of W? W is 12 kilowatt. It is given that W is equal to 12 kilowatt. Kilowatt means 10 to the power 3 watt. Now from this particular formula we can easily calculate Q2. Q2 will be W into COP. So in kilowatt unit this is 30 kilowatt. Now again we also know that is W is equal to Q1 minus Q2. There is another formula. Now W, that is 12 kilowatt. So 12 12 kilowatt, yes, it is 12 kilowatt. Now Q1 minus Q2, that is in the, you see that is there is a printing mistake here. Actually that should be 12 kilowatt, because it is given that 12 kilowatt the work input. So Q1 minus Q2, that actually it should be 12 kilowatt. This is the difference is given, but you know the value of Q2. You know the value of Q2. So then you can calculate Q1. So Q1 will be Q2 plus 12. So this will be 12 actually. Q2 plus 12. So in this way you can calculate Q1. Now we know that T1 by T2 is equal to Q1 by Q2. So from the value of Q1 and Q2 we can calculate the ratio of the temperatures. Another problem regarding the refrigerator. A freezer is maintained at a temperature of minus 10 degrees centigrade. So this is the temperature inside the refrigerator, and the room temperature is 30 degrees centigrade. That means this is the temperature of the surrounding. To maintain the freezer temperature, heat is removed at the rate of 1200 joule per second. You just focus on this particular sentence, that is heat is removed. You are extracting the heat. So this is basically the amount of heat that we are extracting. This is 1200 joule per second. Per second 1200 joule of heat is extracted. So what we have to do, we have to calculate the coefficient of performance and the amount of heat discarded to the surrounding. Now you see that is coefficient of performance, that is defined as Q2 by W. Now W is again Q1 minus Q2. So this particular formula is Q2 by Q1 by Q1 minus Q2. Now we also know that is Q1 by Q2 is equal to T1 by T2. So the same formula can be written in terms of the temperature also. So coefficient of performance is equal to T2 by T1 minus T2. But you see in this particular problem T1 and T2 are given. So we can easily calculate the coefficient of performance. Now, to calculate the heat released to the surroundings, we have to calculate the work done W. Now, W is equal to Q2 by COP. This is another formula that we have already discussed in the previous lecture. Now, you see that is what is Q2. Q2, it has been mentioned, that is 1200 joule per second. This is the amount of heat removed from the food inside the refrigerator. So, Q2 should be 1200 joule per second, and coefficient of performance is this much. So, work done W is equal to this one. This is the work done W. Now, we know the formula, that is W is equal to Q1 minus Q2. So, Q1 is equal to W plus Q2. So, ultimately Q1 appears as 1382.5 joule per second. Now, you see that is the heat which is taken from the food. You are suppose you assume there is some food inside the refrigerator. So, when we are taking the heat from the food, so that particular heat is 1200 joule, but when it is rejected in the surrounding, so that amount is higher. This is 1382.5 joule per second. Now, rest of the problems are very easy. I will again discuss one problem, that is similar to the earlier problem. For example, suppose a heat engine is operated between 137 degree centigrade and minus 43 degree centigrade. So, you see that from this particular data, T1 and T2, we can calculate T1 and T2, and the heat engine receives only 250 kilocalorie of heat per minute. So, this particular value, that is Q1 is given. The value of the Q1 is given. This is 250 kilocalorie of heat. The inventor of the engine claims to develop 12 horsepower with this engine. So, inventor claims that the power is 12 horsepower. Do you agree with this claim? Take 1 horsepower is equal to 746 watt. Now, the point is that from the data you see that is temperature value are given, and another thing, that is Q1 is also given. So, we know Q1 by Q2 is equal to T1 by T2. Now, from the value of the T1 and T2, and as Q1 is given, you can calculate the value of Q2. So, this is the value of the Q2. Now, the work obtained from the engine, that you can again calculate, because this is the value of Q2. So, work obtained should be W is equal to Q1 minus Q2. So, this is 110 kilocalorie. This is the work obtained from the engine per minute, because you see this particular unit is given 250 kilocalorie of heat per minute. So, as we are using directly this data, that is 250 kilocalorie of heat per minute in this particular case. So, value of the Q2 will also be 140 kilocalorie per minute unit. So, work done W, we know the formula is Q1 minus Q2. So, Q1 is given and Q2 has been calculated in this particular step. So, we can calculate W, that is work obtained from this particular engine with this configuration. So, that much work is 110 kilocalorie. Now, 1 kilocalorie is equal to 4180 joule. If we convert to the joule unit, then this will be 4180 joule, and 1 minute is equal to 60 seconds. Now, power developed, that is we know that is power is equal to W by T, that is work by time. Now, what is the value of the work? The value of the work is 110 kilocalorie. That means if we convert to the joule unit, then 110 into 4180 divided by time. Time is 1 minute, that is 60 seconds. So, divided by 60 seconds. So, the unit of the power will be 7663 joule per second. Now, this is basically watt, 7663 watt. Now, you see in the problem, it is mentioned that is 1 horsepower is equal to 746 watt. So, we can calculate the watt unit into the horsepower unit. So, this work is in watt unit. So, if we convert to the horsepower unit, so that will be 10.3 horsepower. But the inventor claims that the power of this engine is 12 horsepower. So, as per the second law of thermodynamics, it is not possible, because for a Carnot engine, the maximum power that can be developed, that is 10.3. So the power of the engine can never be 12 horsepower, so his claim is incorrect. So these are the some examples of the numerical problems which has been given in this particular textbook. So I will request the students to go through the text portion of this book at first. So you just clarify the concepts of the heat engines and refrigerator. You go through the different formula and the significance of those formula. Then you just practice these numerical problems. I hope you have understood the numerical problems which I have discussed in this lecture and the lecture that I have been discussed in the earlier lecture. So I hope you have understood. So I will also thank you for listening my lecture.